Watch a modern industrial robot actively pivoting around storage racks in a dense, dimly lit warehouse. It executes a seamless evasion maneuver, slipping past obstacles. Modern autonomous movement depends on a machine's capacity to process environmental data in real time. While motors and chassis provide the physical capability, the bottleneck for navigation lies in the software's computational logic. A robot operating in the real world receives a continuous stream of high-noise sensor data. The challenge is to translate this raw geometric information into reliable, collision-free trajectory commands. This abstract node graph layout represents the Robot Operating System, or ROS. The ROS Navigation Stack is the specific software architecture designed to manage this data translation. To navigate safely, the system must continuously answer three distinct computational questions. Where am I? What is around me? And how do I get to my goal safely? The stack architecture distributes these questions across distinct probabilistic subsystems, maintaining a constant exchange of data packets across the network. We collaborated with the research team at Royal Research to deconstruct this software stack from first principles, examining how these subsystems interact to produce movement. By layering specialized algorithms, the navigation stack creates a framework for managing the high dimensionality of real-world environments. A robot requires an exact coordinate pose within an environment before it can calculate a path to a destination. To establish this pose, the ROS Navigation Stack utilizes a probabilistic method known as Adaptive Monte Carlo Localization, or AMCL. This 2D floor plan illustrates the AMCL particle filter. At startup, a dense cloud of red dots representing possible robot locations scatters across the map. As the physical robot moves, sensors map the immediate wall geometry. AMCL mathematically discards particles contradicting this incoming sensor data. The surviving particles multiply, causing the cloud to condense tightly around the robot's true physical location. This filtering method accounts for baseline sensor noise and mechanical uncertainty, as the system only rewards the coordinate clusters with the highest probability. AMCL converts noisy hardware readings into a mathematically defined confidence interval of the robot's location. This process relies on having an existing floor plan. If a robot enters an unknown environment without a pre-existing map, it faces a different set of constraints. In these scenarios, the stack utilizes simultaneous localization and mapping, or SLAM. SLAM creates a map of the surroundings while simultaneously using that developing map to track the robot's positional drift. As the robot explores this blank void, its sensor beam dynamically generates an occupancy grid. The algorithm assigns specific values to every cell in the grid, marking them as solid obstacles, free traversable space, or unknown territory. The modularity of the ROS architecture allows developers to swap between various SLAM algorithms based on the hardware's computational budget or the complexity of the workspace. SLAM provides the persistent spatial memory required for long-term path planning. Static maps are only a starting point. Unpredictable environments, like a falling crate, require the system to adapt its route instantly. ROS quantifies physical space for safe traversal using grid-based representations called cost maps. This cost map assigns mathematical penalties to each grid cell based on obstacle proximity. Solid objects radiate dark red for infinite cost, fading to blue for safe space. Pulling back, the global cost map displays the entire static room for long-term routing. A smaller localized square, the global cost map, continuously travels with the robot's center point, identifying new, immediate obstacles. When the local cost map identifies a new obstacle, the stack uses the dynamic window approach, or DWA, to calculate an evasion maneuver. DWA projects a window of physically possible velocities, calculating a fan of curving trajectory arcs branching out from the robot's wheels. The algorithm scores every arc against the local cost map. Trajectories entering a high-cost red zone are instantly deleted, highlighting the single safest curve in green. Cost maps and DWA translate theoretical path planning into physical, collision-free momentum. Managing these simultaneous spatial processes requires an overarching software architecture. The Move base node serves as the executive coordinator for the entire ROS navigation stack. Asynchronous data streams from AMCL, SLAM, and cost maps feed directly into a central Move base hub on an architectural flowchart. Inside the node, A static global route intersects with a shifting local evasion curve, mathematically locking together to form an updated path. The hub pulses, outputting a single velocity vector arrow to the hardware. The synchronization performed by this executive node enables the various subsystems to function as a unified autonomous system. This 3D visualization layers these models together. You see the static map, particle cloud, cost map gradients, and DWA trajectories updating in real time. Operating this stack effectively requires managing system latency, ensuring parallel layers update fast enough to maintain safe movement. Engineering these systems involves calibrating physical sensors and tuning algorithmic parameters to handle the unpredictability of dynamic environments. Robust navigation results from probabilistic localization, persistent spatial mapping, and cost-weighted trajectories. Understanding this architectural framework allows Royal Research to deploy complex autonomous behaviors across a wide range of physical robotic platforms.